Hello students. Now this is the last topic of chapter number 7, transformers. Students, sometimes it is required to convert higher voltage to lower voltage or from lower voltage to higher voltage in an AC circuit. So for this purpose transformers are used. Now students, transformer is a device in which without any loss of power, AC voltage can be increased or decreased. Students, here we are considering an ideal transformer. And so, in ideal transformer, when we change the voltage, then there will not be any power loss. But in real transformer, there is some loss of power. Now students, the transformer with which voltage can be increased is called a step up transformer, and the one with which the voltage can be decreased is called a step down transformer. Students, the principle of transformer is it works on the principle of electromagnetic induction. You have studied about electromagnetic induction in chapter number 6. Now about construction. Now students, here two ways of constructing a transformer is shown. There is a primary coil and a secondary coil which is wound over a soft iron core. So this blue color material is made up of soft iron, and an insulated wire is wound over this soft iron. So this coil is called a primary coil, and an another winding is made from another side, and that coil is called a secondary coil. Same thing you can see here also. This is also a transformer, but here the winding is done in different manner. This coil is called a primary coil, and this is a secondary coil. Remember students, these wires which are used for winding, they are insulated. They are made up of metal, but they are insulated, and this is a soft iron material. So definitely, as there are two coils, there will be a mutual induction. Here also there are two coils, but they are wound over one another, but they are not in direct contact with each other because they are insulated. Now students, the input is given at primary coil. So here an AC is applied, and due to that what will happen? Constantly the current will change because it is an AC source. So current as well as voltage changes. Due to that, what happens? There is a change in the flux of this coil, and as an another coil is wound over it, that flux is linked with the second coil, and due to that an EMF is induced in second coil. Even you can see for this second figure, input AC is given to the primary coil, and when the switch is on, what happens? Due to change in current, what happens? The magnetic field is produced, and due to this soft iron core, that magnetic field which is produced in primary coil gets linked with the secondary coil, and so the flux is linked with the second coil also. And as this current changes constantly, the flux also changes in the secondary, and as a result there is an induction of EMF in the secondary coil, and so we get here an AC. Input is also AC, output is also AC, but only the difference is that the voltage will change. If the transformer is step up transformer, then there will be an increase in the voltage, and if the transformer is step down, then the voltage will decrease. So it is clear that transformer is used either to increase or decrease the AC voltage. Transformer cannot work on DC. There should be compulsory an AC source applied to the primary coil. So now students, once again, a transformer consists of two set of coils insulated from each other. They are wound on a soft iron core, either one on top of the other or on separate limbs of the core. Separate limbs means, you can see here, they are wound over separate limbs, and here they are wound one over the other. One of the coil is called primary coil, and whose number of turns, because the windings are made, so there are number of turns. So primary coil has a number of turns NP, and the other coil is called secondary coil, whose number of turns are denoted by NS. This small s is for secondary and this N is for number, so number of secondary. Now primary coil is the input coil and the secondary coil is the output coil. Means input is given to the primary and the output is taken from the secondary. Now when an AC voltage is applied to the primary, the resulting current produces an alternating magnetic flux which links the secondary and induces an EMF. As I said, when the current passes through this coil, a magnetic flux is linked with this coil due to current, and that magnetic flux gets linked with the secondary coil, and as this flux changes continuously due to continuously change in the current, because it is an AC, and so here as the flux changes, an EMF is generated in the secondary. Students, remember that the frequency of the AC voltage induced in the secondary has the frequency as that of the voltage in the primary. Means here the frequency of AC source is not going to change. Whatever the frequency is there in the primary, same frequency is obtained at the secondary. Only there is change in voltage. Now students, according to Faraday law, induced EMF in primary, that is epsilon P, that is equal to Vp. Epsilon means EMF and V is the potential difference, or simply we can call that as voltage of primary. Here we have taken both are as equal because we have considered that the transformer is an ideal transformer and there is no loss of energy, and that's why epsilon P is equal to Vp. And we have studied in chapter number 6 that EMF is given by minus Np d phi by dt. This is change in flux with respect to time, and this is number of turns of primary. Similarly for secondary, epsilon s is equal to Vs is equal to d phi by dt minus Ns, where Ns is the number of turns of secondary. You can see change in flux with respect to time in both the coils is same. It is because whatever the flux is generated here in the primary, that flux gets linked with the secondary. So change in flux with respect to time is same. Now here we consider an ideal transformer in which the primary has negligible resistance, because the winding of wire may have some resistance, but here the resistance of this wire which we have used can be neglected. So neglecting the resistance, and also all the flux in the core links both the primary and secondary, means whatever the flux is induced here, the same is linked here also. There is no leakage of magnetic field around it. So we will consider that thing also, that there is no leakage of flux due to leakage of magnetic field. Now taking ratio of equation number 2 and equation number 1, we'll get Vs upon Vp is equal to this term upon this term. So when we take the ratio, here you can see this is common, so they will cancel out. So what we will get? We will get Vs upon Vp is equal to Ns upon Np. Minus sign will also cancel. So by taking the ratio, we obtain this equation: Vs upon Vp is equal to Ns upon Np. Let us give this equation number 3. Now for an ideal transformer, input power is equal to output power, means whatever the power is supplied at the input, the same power will be obtained at the output. Only there will be change in voltage and current here also, and voltage and current here also. So now we know that power P is equal to V into I, or I into V. So input power is equal to IP into Vp. This P is for primary because at input side the coil is primary coil, and at output side the coil was secondary coil. So output power is Is into Vs. Once again taking the ratio, that is writing this equation in the form of ratio of currents and the voltages, we get this equation number 4. Students, you can see here this Is is brought towards left side and Vp is brought towards right side. So we got this equation. Now just look at this equation number 4 and this equation number 3. Vs upon Vp is equal to Ns upon Np, that is this, as well as Vs upon Vp is equal to Ip upon Is, so is this. Vs upon Vp is equal to Is upon Ip. So writing these terms together, we will get this combined equation or combined relation. Now students, note above equation, that is this equation, is applicable to ideal transformer in which there is no loss of energy. But in actual transformer, that is real transformer, some energy is lost due to following reasons. Means in a transformer energy is lost, some of the energy is lost, and the reasons are given here. There are four main reasons. One is leakage of the flux, that I have explained you. Resistance of the winding, that also I explained you, that the wires which are used for winding, that wires may have some resistance, so due to that also some energy is lost. Also there is an eddy current. Due to eddy currents there is loss of energy. Where these eddy currents are produced? The eddy currents are produced in this soft iron core. In this soft iron core the eddy currents are produced, and due to that reason what happens, some energy is lost in the form of heat. Students, always remember, this energy is lost generally or mainly in the form of heat only. Then finally, due to hysteresis. We have studied this also in chapter number 6. When there is a change in the current, there is a hysteresis in the material, and due to that reason also there is a loss of energy. So students, I hope you understood about this transformer. So here we complete our chapter. If any difficulty is there, you are free to ask.